Good morning, class. We are looking at chapter 4. Application of derivatives, section 4.2, how derivatives affect the shape of a graph. So we covered maximum and minimum values and now how derivatives affect the shape of a graph. We are going to continue later on to optimization and anti-derivatives. Here's some of the formulas you've seen many times before. As far as differentiation is concerned, we have the definition, we have basic differentiation formulas. We have the product rule, the quotient rule, composite function, the chain rule, power rule, extended power rule, exponential rules, and logs. Also, delta y, which is the rise along the curve as we go from one point to the next, is precisely f of x plus delta x minus f of x, which is this distance, which is f of x plus delta x minus f of x, delta y. And dy is f prime of x times delta dx, where delta x and dx are this distance. Dy can approximate delta y from time to time. So therefore, f of x plus delta x can be f of x plus dy as an approximation. If we call this point a comma f of a, and we use the point slope on that, that is the tangent line. We call the tangent line the linearization or L of x. And they both can give us an approximation nearby this point A. Point A, comma f of a belongs to both the curve and the line, okay? Reminding you of minimum and maximum points, local or relative extrema. A local minimum is the minimum value within some open interval. A local maximum is the maximum value within some open interval. Meaning, if you look at these two graphs, peaks and valleys are local max and mean. Here's local max, local mean, local max, local mean. It's not in the entire domain, but rather in some open interval. Whereas absolute, also known as global extreme values, okay, happen in the entire domain. Absolute minimum occurs at the point C if f of c is less than or equal to f of x for all x values in the domain. Absolute maximum occurs at the point where C where f of c is larger than or equal to f of x for all x values. If you look at these two cases, again, local mean, local mean, local max, local mean. This local minimum is also absolute minimum because no other point has a smaller y coordinate than that. And if you look at this one, local max, local mean, local max. This local max happened to be an absolute max because no other point has y coordinate. A critical point is defined such that you take the derivative, f prime of x equals 0 doesn't exist. The steps are set f, find f prime, set equal to 0, look at where it doesn't exist either. And in the case of the extreme value theorem, also known as closed interval theorem, if you happen to have a continuous function in a closed interval, you find all the critical points by doing f prime is 0 or doesn't exist. You evaluate the function at the endpoints and the critical points. The largest value is the absolute mean, absolute max, and the smallest value is the absolute. So this is what we have seen before. And now the summary of the section, how derivatives affect the shape of a graph, section 4.2, the summary is a function is increasing where f prime is positive and decreasing where f prime is negative. So if you look at this one and assume this curve is a line with a positive slope. If you assume this curve is a line, the same thing with a negative slope, the increasing versus decreasing, so that you can figure out the shape. A critical point has been already discussed, is a point of a function where f prime is 0 or f prime does not exist. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph. So peaks and valleys. A function is concave up where f double prime is a positive. That means f prime is increasing, looking like that. And a function is concave down where f double prime is negative. That means f prime is decreasing, looking like that. This, in essence, can hold water. This cannot. And an inflection point, IP for short, is a point where concavity changes. Inflection points occur where f double prime is zero or f double prime doesn't exist. And if you look at this example, for example, we have concave down here, concave up, and this is the point where the change occurs, known as IP, the inflection point. We said concave up, the graph of f of x lies above all its tangent lines. Look at this one. It's above the tangent line. It's above the tangent line. On the other hand, concave down, the graph of f of x lies below all of its tangent lines on an open interval, so it's below it. Now notice, in this case, f double prime is positive, f prime is increasing. How do you see that? If you look at this curve and draw a couple of line segments as tangent lines, notice this has a positive slope, this has a positive slope, but clearly this is steeper. This has a larger slope than this one. So f prime is increasing. So if you look at the curve, f prime is increasing. If you look at this one, and this one, both of them have negative slopes, but this is steeper. This is more negative than this one. So f prime is increasing. On the other hand, when f double prime is less than zero, f prime is decreasing. So we are talking about concave down. If you, again, do a couple of tangent lines, this one has a negative slope. This is more negative. So f prime is smaller here. This has a positive slope. This also has a positive slope, but this one has a larger slope than this one. So f prime is decreasing. And also an inflection point, a point P on a continuous curve f of x, an inflection point if f of x changes concavity. Notice that we have concave down, then concave up, or we have concave up, then concave down. Either way, the point where the change occurs is the location for an inflection. Steps to curve sketch. In addition to pre-calculus steps, find relative maximum and minimum and intervals where the function increases and decreases. So first do whatever you do for the pre-calculus, okay? That means find intercepts, the end behaviors, and so forth. And then find f prime, set it equal to 0, and do a sign graph to figure out where the function is increasing, decreasing, and whether we have a local extreme. Find the inflection point. How do you do that? Find f double prime, set it equal to 0, and solve for x, and do a sign graph. And do the sign graph to find whether we have an inflection point where the function is concave up, where the function is concave down, and so on. Very straightforward. Finally, we graph. Extreme values of a function are created when the function changes from increasing to decreasing or from decreasing to increasing. In other words, if you look at this one, first it's increasing, then it's decreasing. So that's the extreme value, or more importantly, the peak is the local max. It's decreasing first, becomes increasing second. So in between, we have an extreme value. This is a valley, and that's the local mean. Look at this one, decreasing, increasing, decreasing. Local mean, local max. Increasing, decreasing, increasing, decreasing. Local max, local mean, local max. And so the theorem says a function is increasing where f prime is positive and decreasing where f prime is negative. Okay. Now we can prove that, and the proof is by what we call the mean value theorem. We have the details in calculus when you're not responsible for the proof. But the synopsis of that is this: if f is a continuous function in a closed interval of a to b, differentiable in an open interval of a to b, and then f prime of c equals f of b minus f of a over b minus a, which means if you have a curve and that curve from a to b is continuous and differentiable, it's a nice and smooth curve. If you connect those 2 points and continue indefinitely, that creates a line known as a secant line, and this is its slope. Somewhere in between B and A, there is a point C such that the line has a slope equal to that tangent line, which means parallel to that secant line. That's the concept. If you do the cross product, you get this one, by the way. This is the same as that. But how does that help us with the proof? The meaning of increasing, remember, when x gets larger, this means getting larger, y gets larger. So normally when we have A and B, we are assuming, and if you look at this one, B is on the right side of it. So B is larger than A. So for sure, B is larger than A. So let's assume F prime is positive. So if F prime is positive and B is on the right side, obviously if F prime of X is positive, that means at any point, that means F prime of C is positive. That means this expression is positive, right? Now, if this expression is positive and B minus A is positive, because B is larger than A, right? Then the numerator must be positive, and therefore f of B must be larger than f of A. That is the proof of increasing. I hope everybody is following that. Again, very straightforward. It's you're not responsible for that, but that should be pretty straightforward. What is the first derivative test? Well, when y prime or f prime is positive, curve is rising. If it's negative, the curve is falling. What creates at top a peak known as a local max. However, if it's the other way around, first it's falling, then it's rising. Again, it creates a local, an extremum, but this one is a local mean. So y prime or f prime equals 0 or does not exist. Those are possible locations of maximum and minimum. How do you find them? Use sign graph for this test. How do we do that? I'll show you as we look at an example shortly. What about test of concavity? Well, y double prime or f double prime is positive. The curve is concave up, looking like that. If it's negative, it's concave down, looking like that. Where it's 0 or doesn't exist, those are possible inflection points where concavity changes. So a function is concave up, where f double prime is positive, means f prime is increasing. And it's concave down, where f double prime is negative, means f prime is decreasing. How do you figure it out? Use sign graph. Is that the same as a second derivative test? Absolutely not. The second derivative test gives you half of the information of the first derivative test. That means you find f double prime and evaluate it at the critical points. What are the critical points? Remember, f prime equal to 0. And you plug in. You plug in the critical point. If that gives you a negative value, graph is concave down. So therefore, x equals that critical point must be a local max, looking like that. On the other hand, if it's positive, graph is concave up, looking like that. That critical point must be a location of a local minimum. That's what it's all about. Synopsis of everything you need to know, and we are ready to graph. However, I want to remind you of something you've seen in algebra. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. So a function of polynomial is in the form of a sub n, x to the power of n, all the way to a sub 0. This a sub n, x to the power of n is called the leading term. N is the degree, a sub n is the leading coefficient, and therefore, if you look at the following class, when you're dealing with an even power, okay, the graph looks like y equals x squared or y equals minus x squared. Which one is the case? Well, if a sub n, the leading coefficient is positive, it looks like y equals x squared, meaning the end behavior belong to the first and second quadrant, meaning whether x approaches negative or positive infinity, f of x in both cases goes to positive infinity. If, however, a sub n, the leading coefficient, is negative, it looks like y or f of x equals minus x squared. That means whether x goes to negative or positive infinity, f of x or y goes to negative infinity. That means the end behavior gives us the third and fourth quadrant. On the other hand, if we are dealing with the odd power, then the end behavior either looks like x cubed if a sub n is positive, or if it's negative, looks like minus x cubed. In this case, x goes to negative infinity, so does y. X goes to infinity, so does y. On the other hand, here, when x goes to negative infinity, y or f of x goes to positive infinity. If x goes to infinity, f of x or y goes to negative infinity. This is known as the end behavior. Now, we have also a theorem known as behavior near a zero with the x-intercept. A zero, x minus c to the power of m, has a multiplicity m. That means it repeats itself how many times? Depends on this exponent. If m is odd, f crosses the x-axis at c0, and if it's even, does not cross the x-axis at c0. So look at this one. So the graph showing three different polynomial functions with multiplicity 1, which is odd, 2, which is even, and 3, which is odd. So crosses, not this one. Okay. Now, what is the difference between these two? The higher the multiplicity, the flatter the curve is at the 0. The sum of the multiplicities is the degree of the polynomial function. This is reminding you of what you have seen in algebra, so it will help you with the graph. We want to graph y equals x cubed minus 3x squared plus 4. And I'm going to show you how to graph it using pre-calculus, and then we pay attention to more details. Number one, you need the intercept. So the y-intercept is 0, 4. Number two, you need the x-intercept, and you put it in a factored form. It's given to us, so clearly this is negative 1, 0. This is 2, 0. So we have all the intercepts, and this is x cubed. We have the end behavior, so we should have no problem graphing it. So we have negative 1, 0, 2, 0, 0, 4. Also notice this means that's multiplicity 2. And I put an arrow, let me use a different color. I put an arrow here, means it can't cross. And this one, tells me the end behavior, right? Looking like x cubed. So if I were to graph it, it'll look like this. It hits this one, comes back up, hits this one, comes back down, and I'm done. The only thing is, what happens here, everybody? Where is the maximum? The maximum may be this point, maybe on the right, maybe on the left. We don't know it unless we do calculus. So this is the idea behind graphing this without calculus, okay? In other words, you could graph it. It's not a big deal. But let's make it with more details. So the very first thing is to take the derivative, which is 3x squared minus 6x. And to set this equal to 0, we factor the 3x out. And x is either 0 or 2. And now to do the first derivative test, we have to do the sine graph. So we plug in this number. This goes from, this is a number line from negative to positive infinity. You put 0 and 2 in order. So over here, we have 0 and 2. Now you do TPs. I hope you remember test points, right? TPs. And so to the left of 0, you can go with -1. Between 0 and 2, you go with 1. And over here, you can go with 3. And you put that into y prime, either in this format or the factor form, whatever is easier. What I want you to understand is this. Because this has exponent 1, this has exponent 1, they will alternate. And pay attention, this is positive, nothing changes. If it were negative, everything would change. So all you have to pick one of them. One is the easiest point. If I put 1 here, this is positive, this is negative. So the product of positive and negative is negative. So it's negative. If it's negative, okay. And if I put -1, I start with -1. If I put -1, this makes it -3. If you put it into this one, 3 times -1 squared minus 6 times -1 makes it positive. So this is positive. And again, they will alternate, class. If you do, one of them is good enough. But just let's plug in 1. If you, again, whatever is easy, if you plug it here, you get 3 minus 6 negative. And if you plug it here, you get positive, negative, positive. So it's very straightforward. I like to throw in arrows. It helps me see that, okay, positive arrow up, negative arrow down. So increasing, decreasing, increasing. So what does it mean increasing? That means from negative infinity to 0, union 2 to infinity is increasing, and 0 to 2 is decreasing. As it changes from increasing to decreasing, this is the point of local max. As it changes from decreasing to increasing, it's a local mean. So you plug in 0 into the original function, you already have 0, 4. So 0, 4 is the location of a maximum. What is the maximum value? The y coordinate. So we don't have to evaluate, it's already done. Again, arrow down, arrow up, negative, positive, decreasing, increasing, this is a local mean. 2, you could put it back into original function. You already have at 2, you get 0. So the local minimum is equal to 0 at the pair 2, 0. And as I mentioned, it's increasing here, meaning negative infinity to 0. Also here, union 2 to infinity. It's decreasing here, meaning from 0 to 2. So you're right there. All right. So since I don't have room, I'm going to go to the next page. I'm going to write the function, the factored form, and I'm going to do the second derivative test You don't need to. I can't emphasize this enough. I just want to show you why I don't actually do the second derivative test for graph because it gives you only half of the information. Because y prime is given, now we can find y double prime, and here's the critical points that we found. The y double prime is what? 6x minus 6. And you just plug in 0 to see it's positive or negative, plug in 2 to see it's positive or negative. If I plug in 0, I get negative 6. It doesn't matter, negative 6 or negative 10,000. You're just paying attention to the sign. Because it's negative, the graph is concave down. Okay, looking like that. Because it's negative, it looks like that. And if it's concave down, this is local max. So graph is CD, concave down. 0, 4 is a local max. On the other hand, if I put the 2 in there, I get positive 6. Again, it doesn't matter positive 6 or positive 6,000. I'm just interested in the sign, which gives me this. And what is this? Local mean. So graph is concave up 2 and put it back into that 2, 0 is the location of it. Local mean. Now, where is the function increasing? Where is the function decreasing? We don't know with the second derivative test. That's why it's an excellent tool for applications, not a good idea for graphs. All right, we want to find inflection points. So again, remember what we did. We have the function. We have y prime. And since we did y double prime in the previous page, we're going to use it here. Okay. Set it equal to 0. Okay. And x becomes 1. And remember, if it's negative, concave down. If it's positive, concave up. So let's put it on a number line that we're going to do the sine graph from negative to positive infinity. We are going to put this here. And at this point, f double prime is 0. Now we do the test point. Obviously, the easiest point, let me write down TPs. So TPs, the easiest point to the left of 1 would be 0, and to the right would be 2. So plug in 0 into what? Into y double prime. See, that's what your sine graph is on this function, f double prime. That's why you put this function at top. And x was from negative to positive infinity. So plug in, and you just want the sign, negative. If you plug in 2, you get positive. What does it mean? Concave down here from negative infinity to 1. Positive means concave up here from 1 to infinity. Because of the change, 1 is a location of a inflection point. So what do you do with 1? Plug it into the original function. This one or this one makes no difference. If you put 1 here, you get 2. If you put 1 here, 1 minus 2 is negative 1 squared, you get 1. The product is 2. So 1 comma 2 is the IP, the inflection point, everybody. Okay, so we have the inflection point. All right, we want to graph this. So I'm going to put all the information we have. There's nothing brand new here. Here's the function. Here's the factored form. Here's y prime. Here's y double prime. Everything was found in previous pages. Here's the intercepts. Here's where it's increasing, where it's decreasing. Here's concave down. Here's the IP address. Here's concave up. Let's do the summary. So minus 1, 0, it's here there. 0, 4 is there. Because it's a maximum, we put an arrow, meaning that's the maximum it can't cross. 1, 2 is the IP address. X-intercept at 2, 0, and it happened to be the minimum. Again, we go there. That's good enough. We have the end behavior. But extra point, if you put 3 here, you get 4. This one, you get 1 squared, which is 1. So 3 comma 4 is another point. And again, x cubed gives you the end behavior, and you have it. You're done. Very simple, everybody. And we're done with the graph. Okay. The difference is it's more precise, meaning look at where the function is increasing, decreasing, increasing. Where is the function? Concave down. Where is the function? Concave up. Where is the inflection point? Where is the max? Where is the mean? Everything is no. We're going to graph f of x equals half of x to the power of 4 minus x. To do that, again, I'm going to go back to algebra and do it without calculus, a rough sketch. And to do that, it's very simple. All you have to find the intercepts. To find the intercepts, I'm going to set this equal to 0 and take out 1 half x squared. I get x squared minus 2. This gives me 0, just so you see what happens here. This gives me x equals 0. This gives me x squared equals 2, which means plus minus square root of 2. So I have the following intercepts. And I'm going to use that to graph. That's all I'm going to do for now, which means the graph looks something like this. By the way, square root of 2 class is about 1.41, just to give you an idea. 1, 2, 1, -2. And so let's graph the points that we have. We have 1.41 roughly. It's not perfect, it's here. Negative is here. 0, 0 is here. Now go back and I'll show you that when you look at x squared, multiplicity is 2. That means 0, 0 has a multiplicity 2. And I'm going to put an arrow here, meaning it can't cross, everybody. And I'm going to look at this one and say, well, 1 half x to the power of 4. So the end behavior is just like x squared, first and second quadrant. So if I want to graph this, I'm going to hit this x-intercept. And I don't know when, at some point has to come back up, hit this x-intercept, but it can't cross. I'm going to go back down, has to come back up, hit this x-intercept, and go up. Now, one of the things we did in pre-calculus, we would discuss the even and odd. I hope you can see that if you plug in minus x, you get f of x. So this is an even function. An even function means what? Means symmetric with respect to the y-axis. That means the right half and the left half must be identical. Okay. And as you can see, the zeros are, right? The left half and these 2 points must be the same. This is a terrible sketch, but you get the picture. Now we are going to actually use calculus to make this look much better. So I'm going to erase my work, everybody. All right, so we want to go with the first derivative test, and therefore we are going to go with CPs, and therefore we're going to go with f prime of x. And that means 1 half times 4, 2x cubed minus 2x. To set this equal to 0, we need to factor, so we're going to factor the 2x out. first, this x squared minus 1 becomes x plus 1, x minus 1. Therefore, the critical points, x is 0, x is minus 1, x is plus 1. So we have 3 critical points. So we are going to go with a number line from negative to positive infinity, and we put those 3 numbers in order. At negative 1, 0, and 1, all of them, this becomes 0. We are going to use test points, but before we do that, please understand that they will alternate. The reason why. 2 is positive. It's important that this is positive class, so it doesn't change anything. X has exponent 1, x plus 1 has exponent 1, x minus 1 has exponent 1. They will alternate. If any of them has exponent which is even, then both sides will be the same. Let's assume this was x minus 1 quantity squared. So at 1, both sides will have the same sign, okay? But in this case, they will alternate. Again, I'm reminding you of what you should know from algebra. So we have minus 2 here, minus 0.5 here, 0.5 here, 2. Those are test points, everybody, test points. This test minus 2, you can put it here, you can put it here, whatever is easier. If I put it here, it might make it easy. 2 is positive as no bearing. So this is negative, minus 2. Minus 2 plus 1 is negative. Minus 2 minus 1 is negative. So negative times negative makes it negative. If this is negative, the rest of them alternate. Or just plug in and find out. Negative 0.5. Negative, this makes negative 0.5 and positive 1 positive, negative 0.5 and negative 1 negative. So we have positive, okay, I'm sorry, negative, and we have positive, and we have negative. Therefore, the answer is positive. In any event, let me throw in the arrow. So again, what it means is that negative means decreasing, positive means increasing, decreasing, increasing. So the function is decreasing, for example, here and here, meaning from minus infinity to negative 1 union 0 to 1, and it's increasing here as well as here. So from a negative 1 to 0, union 1 to infinity. Now, as the reason I put the arrows, arrow down, arrow up, you can see that it looks like that. So this is a local mean, local max, local mean. So the local mean, there are 2 of them at negative 1 and at positive 1. What is the y coordinate? Put it back into the original function. So 1/2 x to the power of 4 minus x squared. Whether I put plus or minus 1 makes no difference because it's being raised to the power of even. So this is 1. So we get 1/2. This is 1. We get 1/2 minus 1 or negative 1/2. So the local mean is equal to negative 1/2 at x equals plus minus 1. The way we write it is in this format. 2 pairs, negative 1 comma negative 1/2, 1 comma negative 1/2. Local max is at 0. Look at the arrows, arrow up, down. And we put it in, we already know 0 gives you 0. So local max is 0 at 0, 0. As I mentioned, increasing from negative 1 to 0, union 1 to infinity, decreasing here from minus infinity to minus 1, union 0 to 1. So that should be pretty straightforward, everybody. All right. We are going to go with the inflection point. So I'm writing the function, its derivative, and everything we found in previous pages. F double prime is 6x squared minus 2. You set it equal to 0. And you get plus minus 1 over square root of 3. The reason is because 3x squared is 1. X squared is 1/3, and x is plus minus 1 over square root of 3. So possible inflection points at those 2 points. We do the sine graph. So when we do the sine graph, we put those numbers here at the bottom and 0 at the top. So we are talking about negative 1 over square root of 3 makes f double prime 0. Positive makes it 0. And if you use TPs, test points, I hope you recognize that square root of 3 is 1.7. So 1 over 1.7 is less than 1. So you would use 1 here, 0 here, negative 1 here. However, they will alternate again in sign because this has degree 2 and has 2 solutions. Okay, that means if you were writing it as a factor, they would each one having the odd exponent. And so the easiest point would be 0. If I put the 0 into f double prime, I get minus 2. Put 0 into f double prime, I get minus 2. So this is negative. If this is negative, they will alternate. Okay. I mean, you can plug in minus 1, makes it 6 minus 2 positive. Okay. And so what happens is clearly positive means concave up, negative means concave down, concave up. So negative from here to here is concave down. From minus infinity to minus 1 over square root of 3 union 1 over square root of 3 to infinity is concave up. So we write those. Because of the change, positive goes to negative, negative goes to positive, both points represent inflection points. You need to find the y coordinate for each case. And so what do? You put them into the original function. And whether you put positive or negative makes no difference. The reason it makes no difference is because plus minus to the power of 4 or 2, both of them become positive. First, 1 over square root of 3 to the power of 2. I hope you recognize this one as 1/3. Therefore, raise it to the power of 2 and to get to the power of 4, right? It becomes 1 over 9. So 1/2 times 1 over 9 is 1 over 18 minus 1/3, which is 6 over 18, becomes minus 5 over 18. This is basic math we are dealing with, okay? Therefore, there is a couple of inflection points as follows. Plus minus 1 over square root of 3, comma, minus 5 over 18. I'm going to change both of them to decimal representation. This is plus minus 0.6. This is minus point, let's say 3 for the sake of graph. Okay, everybody? And so we are ready to move on. I'm going to write everything that we found in a table so we don't feel lost. And I'm going to start with the intercepts. And remember, square root of 2 is about 1.41. So this is 1, this is negative 1. So negative 1.41 is about here, positive 1.41 is here. Those are the two x-intercepts. Maximum happens at 0, 0. We put an arrow anytime you have a max or mean. The IP address, we're going to go with negative 0.6, negative 0.3. So roughly here and roughly positive 0.6, negative 0.3. So we get those 2 points. Okay, rough. It's not exact. Okay. A minimum at negative 1, negative 1. So negative 1, negative 1/2. This is positive 1, negative 1/2. And each one takes an arrow. Okay. Putting them all together. That's the graph, everybody. Okay. I hope everybody's fine with that. Now, the function is decreasing here, increasing, decreasing, increasing. It's concave up, concave down, concave up, inflection points, local max, local mean, local mean. These two are also absolute mean because no other point has a smaller y coordinate, everybody. So I hope everybody's clear on that. Let's look at this application. The number of bacteria in millions present in a culture at time t in hours is given by n of t equals 2t times 5 minus t squared plus 14t plus 100. Find the initial population. Initial population means t0. So if I put 0 here, clearly this becomes 0, this becomes 0. The answer is 100. 100 what? Millions of bacteria, okay? At what time before 10 hours will the population be maximized? First, the function, it makes it easier if I distribute and I get 10t minus 2t cubed and combine these two and put it in descending order. I want you to pay attention to the interval. It says before 10. Why is it from 0 to 10? We're talking about time, so it starts from 0. We don't have a negative. And it says before 10. That means 10 is not included, which makes this half closed, half open, which means when we go through the process, we must know what happens at 0. At one of the endpoints, we already have the number. So now the next thing is, of course, at 10, we don't evaluate it because it's not part of it. We have to take the derivative n prime of t. N prime is minus 6t squared plus 24. In order to set this equal to 0, we are going to factor the negative 6 out. T squared minus 4 becomes t plus 2t minus 2. We have two answers, plus minus 2. And when we look at the interval, we can only go with positive 2, right? So we have one critical point. Before we move on, if we happen to have an open interval and one critical point, when you do the test, okay, local becomes absolute. If it's a local max, it's an absolute max. If it's a local min, it's an absolute min. I want you to know that. In any event, so what do we do here? I'm going to show you both the first as well as the second derivative test. The first derivative test requires the sign graph. So we have t that goes from 0 to 10, and we put the 2 here, and we have n prime of t. Now, the test points obviously are easy points, TP. Test points over here would be 1 over here. You can even test the number 10 for testing, okay? If you put 1 into n prime, if it's easier, just use this one. If it's easier, use this one. 1 makes this minus 6 and 24, positive 18. And then they will alternate class, okay? But if you have doubts, put 3. 9 times minus 6 minus 54 plus 24 is minus. And so let me throw in the arrows. Let me throw in the arrows. So arrow up, arrow down means maximum occurs at t equals 2. Okay, maximum occurs at t equals 2. And so this is the first derivative test. However, this application, and what would be the second derivative test? Ignore that, completely ignore that. When you find this, put that into the second derivative. Now, what is the second derivative? Go back here. N double prime is minus 12t. Now plug in all you want if it's positive or negative. So plug in 2 and it becomes negative 24. Whether it's negative 24 or negative 2 or negative 2000, you're just interested in the sign. Negative means concave down, means maximum. Concave down looks like that, everybody. So it means maximum occurs when t is 2. What is the maximum? Put the 2 into either this one or this one. It's easier to evaluate it with this one. It makes no difference which one you put in. But do the one that gives you a faster number. This is 4. 5 minus that is 1. So this whole thing is 4. This is 28, 32, and 100. 132 million. And make sure that this number is larger than n of 0, okay? And the maximum population would be 132 million bacteria at t equals 2 hours. Sketch the graph of f of x equals x minus 2 to the power of 2/3 plus 1. And I hope you remember we discussed this with the closed interval and what was going on. To better understand this, we are going to rewrite this as cube root of x minus 2 quantity squared plus 1. So you recognize this as a cube root. And how would you graph it? You would graph it with transformation. I want to remind you of algebra. So what is y equals cube root of x? You should know the graph looks like this. The next thing, minus 2. So cube root of x minus 2 means shift right by 2 units. Take it to the right by 2 units. This is the graph. The next one is to square that. What is the effect of that? Let me remind you. The portion which is above the x-axis is positive becomes larger. The portion below the x-axis, which is negative, when you square it becomes positive, flips over. So it looks like this. And your x-intercept hasn't changed. Finally, move up. So up by 1 unit. Something goes up by 1 unit. When it goes up, this has coordinates 2, 1. So it's very straightforward. I hope it's clear to everybody. So this was graphing it using prior knowledge of mathematics. Very simple. Let's make it look better with calculus. So the very first thing, again, that's the function. We are going to find f prime and assign graph and see what's going on. So to take the derivative, and we had done that again before. This one is easier, 2/3 x minus 2. to the power of 2/3 minus 1, which makes it negative 1/3 times the derivative of the inside, which is 1, because we want to use the first derivative test. We're going to rewrite this as a 2 over, so in other words, take this down and make it cube root of x minus 2. Now, f prime is 0 when the numerator is 0, because it's a fraction. Doesn't have any solution because the numerator is a number. F prime doesn't exist when the denominator is 0, and clearly that means x equals 2. So there is a critical point, everybody. X equals 2. So let's plug in. We are going to go from negative to positive infinity. Our critical point is 2, and we want to see what happens to f prime at 2. It does not exist. So what happens to the left and right? You plug in numbers, easy test points, TPs. So over here would be like 1, over here would be like 3, and you put it into f prime of x, either this one or that one, doesn't matter. So if I put the 1 here, so we want to see what happens to this. If I put 1 here, I get negative 1. Cube root of negative 1 is negative 1. So 2 over 3 times negative 1 is negative. And you have to check the 3. 3 minus 2 is 1. Cube root of 1 is 1. So 2 is positive, 3 is positive, 1 is positive. Everything is positive. So negative, positive. What does it mean? Let's throw in the arrows. Arrow down, arrow up, arrow down, arrow up. This is looking like that. Local minimum occurs at x equals 2. So if I plug in 2 into this one, or this one makes no difference, this goes to 0, this is 1. So local mean is 1 at x equals 2, or better yet, 2 comma 1 again. 2 easily gives you 1. I hope you see that. We don't have a local max. What about increasing, decreasing? The function positive or arrow up increasing from 2 to infinity, arrow down or negative decreasing from negative infinity to 2. So first derivative test not only gives us intervals of increasing, decreasing, it also gives us local extreme. All right, let's go with f double prime. To go with f double prime, I'm going to differentiate this one, not this one. It's easier. So 2/3 times negative 1/3 gives us negative 2 over 9. And this one to the power of minus 4/3. And the derivative of the inside is 1. You don't have to. So one more time. 2/3 times negative 1/3 is negative 2 over 9. Same thing to the power of minus 1/3 minus 1 is minus 4/3. The derivative of the inside is 1. Now, I'm going to take this down, make it positive exponent 4/3, and write it as a cube. Now, you may notice that the denominator, whatever this is, has exponent 4, which is an even exponent. Everything becomes positive. This is positive, and this is negative. So this is always negative, except at x equals 2. Why? Because at x equals 2, the denominator becomes 0. It's undefined. So if it's always negative, it's always concave down. But is it from negative to positive infinity? The answer is no. Instead, you say from negative infinity to 2, union to 2 to infinity. That's how you write it. Now, you don't have to do the sign graph. I just do it for the sake of those who are interested in seeing it. Again, no need for sign graph because it's always negative, right? But we proved it. But F double prime is zero, no solutions because the number negative or positive makes no difference. F double prime doesn't exist when the denominator is zero. And you put the, again, number line from negative to positive infinity, and this at 2, it doesn't exist. And if you go with the test points, TPs, put 1 here, 3 here. If you put 1 or 3 makes no difference, makes this one cube root, whatever to the power of 4 positive. So negative over positive times positive, it's negative. So that's the same result. Again, you don't have to do that, but just in case. Now I want to put all of this information and graph it. And notice I haven't discussed the intercepts yet, and I'm going to discuss it again. So first and foremost, I'm going to write the function in both formats. I'm going to write where the function is increasing, decreasing, concave down. The minimum value, we want to find the intercepts. To find the intercepts, if you set x equal to 0, you get -2, cube root of that. Okay, squared, you get 4. So cube root of 4 plus 1. And this is about 2.6. This is for the sake of graphing, everybody. There is no x-intercept. Why not? I'm going to remind you again why it doesn't have any x-intercepts. X-intercept, you said f of x or y equal to 0. We're going to move the 1. Because it's x minus 2 to the power of 2/3, I'm going to raise both sides to the power of 3. Left side is x minus 2 squared. Right side is -1 cubed, which is -1. This is always positive except at 2. This is always negative. That creates no solutions. That's why we don't have any x-intercepts. And now we are ready to sketch the graph. So what do? First, we write the points that we have. This is what? 0, and instead of that, I'm going to say 2.5, 2.6 roughly. We have the minimum at 2, 1. And definitely we need a couple more points just to be on the safe side. And we're going to go with easy points. For example, if I plug in 1, and you can take it to this one or this one, either way. If I put 1 here, 1 minus 2 makes it -1. Cube root is -1. Square root +1, 1 and 1. This gives you 1, 2. If I put 3, I get the same thing because 3 minus 2 is 1, cube root is 1, square root is, so 3, 2. And I put -1, meaning use a calculator. Okay, I don't want to use that point. So why am I using -6? Again, an easy number. If you plug in, you get -8. What is cube root of -8? -2 squared is 4 and 1, 5. What about 10? If I put 10 minus 2, 8. Cube root is 2, 2 squared is 4, and 1 is 5. So take the easy point so you can do it in your head. Now, the first one, 0. Again, I'm going to go with 2.6. This is 1. This is 2. 2.6 somewhere here. Okay. The next one is 1. And 2 is here. The next one is 2. And 1 is here. The next one is 3. And 2 is here. This is the minimum, by the way. This is 3 comma 2. You can use the rest. Okay. Minus 1, 3.0. It is a little bit about 3. Minus 6 and 5. 10 and 5. And now put them all together. That's the graph. Obviously, the function is decreasing here, increasing here. Also, the function is concave down here, concave down here. So all the information that we have come up with, it shows as far as the graph is concerned.